Okay, so we're going to start talking about light. And the reason why light is important is because it, believe it or not, ties to all that stuff that we've been talking about with the electrons and the electron configuration. And I know that doesn't seem like that would be the case, but the two are intricately tied. Knowing where the electron's at, and then the movement of electrons between different orbitals is what's going to generate light. Whether it be that we're injecting flame into or injecting a salt into a flame with a spray bottle, or whether we're doing an oxidation of luminol to produce that blue glow, or a glow stick, we've broken a glow stick. All that is going to be tied to where the electrons are located in different compounds or in different ions or in different atoms. Um, and so when we talk about light, we really have to understand what it is. And light is really basically just small massless bundles of energy. We call those photons. So when you hear of a photon, it's just a little packet of energy. It's got a very discrete or very set or determined amount of energy to it. And we know that, when we start thinking about light, we start thinking about colors. We might think about the rainbow, where, there are red, orange, green, blue, indigo, violet, all those different colors in that visible spectrum, and we're going to talk about that. But in reality, there's a lot more to photons than just the visible, and we use those quite frequently in chemistry. Although we're going to focus a lot on the visible for right now. So when we talk about this, light's kind of weird. We talk about the idea of light being comprised of massless particles of energy. It's weird that we would think that there would be a particle that would have the property of a wave. And we don't think of particles or things as normally behaving in this way. When we know a wave, we know that we get these peaks and we get troughs, and they tend to be repeating and regular, and they tend to be continually moving. Um, and so we know that we have these things. We have this conceptual picture of what a wave would look like, and we certainly don't associate that with like a bullet or a baseball that we throw, or us as we walk down the sidewalk. We certainly don't visualize us as having a wavelength or having a frequency. And so the idea of a particle having those properties of of light is kind of a strange thing. So, just a couple properties that we want to talk about is, the idea that if we're going to go from one peak to one peak, we call them, they're also called crests. But if we go from one crest to one crest, or one peak to one peak, that distance is wavelength. Now, I picked peak to peak. I could have picked trough to trough. I could have picked the same point on two adjacent waves, and the wavelength would be the same for all of them. And so waves have a wavelength, so do photons, because they're particles that behave like waves. There's also a frequency, so this is continually oscillating and moving to the side. So if we look at here, if you notice in the second one, all right, or the third one, there are going to be three complete waves where we start and go from a peak, and we end up at another peak. There are going to be three of those units in the same distance as this one at the top. So in other words, there are more peaks and troughs per second than there are here in the top. And we call that measure of, how many peaks and trough units would pass by in a second. We call that the frequency. So if we talk about the idea of, low frequency would have very few peak and trough units pass through, where a high frequency would have a lot pass through that time, through that period in that, or pass by in that amount of time. So high frequency, low frequency, long wavelength, short wavelength. Okay? Because the distance between peak to peak here is going to be about a third of what it is up there in the top. And the wavelength and the frequency are very important for us understanding how much energy is being carried by that particular photon. And so what I mean by that is, as the wavelength gets larger, the energy that that photon is transmitting or that is carrying, all right, is going to get smaller. So large wavelength or long wavelength is going to correspond to a lower energy photon, carrying less energy. Frequency, however, is directly proportional to energy. So the higher the frequency, all right, the larger the amount of energy that that photon is carrying. So frequency is directly dependent on or directly proportional to the amount of energy that the photon possesses, while the wavelength is inversely proportional to the amount of energy that the photon is carrying. So we can use wavelength and frequency to help us determine how much energy that photon might have or might be carrying. And if we think of this in terms of the visible spectrum, the visible spectrum are all the different types of photons that our eye is sensitive to. And there's red, orange, yellow, green, blue, indigo, and violet, where violet is the purple end and red is the red end. Sorry. So the visible spectrum is there. It's continuous. So the colors transition into one another. So red tends to be the lowest energy photon and violet tends to be the highest energy photon, which means that the wavelength for the violet would be shorter and the wavelength for the red photon would be longer. If we were thinking about this in terms of frequency, all right, we said violet's the highest energy, so it's going to have the highest frequency. And red is the lowest energy, it's going to have the lowest frequency. So low frequency, long wavelength, high frequency, short wavelength for violet light. All right, everything else is in between. So blue is going to have a shorter wavelength, a higher frequency than orange will have. Green will have a higher frequency and a longer wavelength than yellow photons would have. And that visible region of the spectrum fits within the larger, grander part of the electromagnetic spectrum, or fits in with the larger, grander electromagnetic spectrum that exists, which has all the different photons in it, starting with gamma over here and radio here. Now notice that this is actually flipped from before because gamma rays have the highest energy and radio waves have the lowest energy. You know, and you might not think of radio waves as being photons, but radio waves are photons. There are photons of radio frequency energy. And you have a radio transmitter probably very close to you right now if you're not holding it in your hand, and that is your cell phone. It's putting out large amounts of radio waves right as you speak. They're very low in energy. They actually cause electrons to rotate. Probably not even that, to be completely honest. Radio waves don't have a lot of energy. They don't cause a lot to happen on the atomic scale. Gamma rays, on the other end, are very high frequency, high energy. All right. Gamma rays can break bonds, chemical bonds in a covalent compound. They can cause electrons to be ejected from an atom. They can ionize. So sometimes you hear called ionizing radiation. You know, people say you shouldn't go out and lay in the sun to get a suntan, right? You should put on sunscreen. Why? Because there's ionizing radiation. It can cause ions. It can produce radical species that can damage your DNA, and that can lead to uncontrolled growth of weird tissue that we would call a tumor, and that can lead to skin cancer. And so, you know, ionizing radiation normally would be the far end of the ultraviolet, the X-ray, and the gamma ray. They're very high energy. They can cause all sorts of stuff to happen on the molecular scale. And then you get into the visible region. Visible region is here. The purple end on one, purple side on one, the red on the other, red being the lowest energy, longest wavelength, smallest frequency. And then we have infrared, microwave, and radio waves. All right, and so that's the whole electromagnetic spectrum. Now we've talked about what radio waves do. Microwaves actually cause molecules to rotate. Some communications with cell phones is on the high end of the microwave, although most of it's in the radio wave spectrum, but there is some communication in the microwave. Infrared causes bonds to vibrate. And so you get vibration of molecules. It's almost like a dance. So you can start to see that atoms will start to dance whenever you shine infrared light on them. And infrared is another name for heat. So you feel heat. Heat is infrared radiation. And then in the middle is visible. Visible actually causes the electrons to move around. It's a little more significant of an effect than what you would see with infrared or microwave, but not nearly what we see with gamma or X-rays. We're hit with visible light all the time, and yeah, it's causing our electrons to move all over the place, but they go back to where they belong. So. All right, so when that visible light strikes, what does it cause? And we're going to break back to, we talked about the idea of, the atom is a little more complicated. I talked about that, and we talked about orbitals and said it's a little more complicated than what we would likely think it would be. We're going to jump back to something actually that's wrong, but is instructive, and that's what we call the Bohr model of the atom, which is the nucleus in the center, sort of like the sun, and then the electrons in this orbit, all right, around the sun, sort of like a solar system model. And the orbit that's closest to the nucleus, we call that n equals 1, and then n equals 2, 3, 4, and 5. And so here's what happens. So imagine that we've got an electron at n equals 2. So what elements do we have? Lithium and beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon are the ones that have their outermost electrons in the n equals 2 energy level. And imagine we've got an electron there, and then suddenly a red photon strikes that particular atom. It absorbs that photon. It takes in the energy from that photon. It will cause the electron to move, if it's a red photon, to n equals 3, which is further away from the nucleus. When it does that, okay, it had to take in energy to get there. And it took in the energy in the form of absorbing a photon, but that electron doesn't want to stay at n equals 3. Its home is n equals 2. So it wants to come back down to that home. And we call that home the ground state. And we call the place that the electron is moved to when it absorbs a photon the excited state. So when it's got the electron in n equals 3, when it's moved to n equals 3, it's in the excited state. Then it comes back down to the ground state, and when it does, the energy that it had at n equals 3 is now no longer with it. So where does that energy go? It causes a photon to be given off, okay, or emitted. So when we move from a high energy to a low energy orbital, our energy will be given off. When we move to a low energy level and we move to a higher energy level, energy must be absorbed. If we think about that in terms of distance, if we have an electron that moves further away from the nucleus, we have to be adding energy to it. All right, a photon must be absorbed. And if we have an electron moving from far away from the nucleus to close to the nucleus, well, it's got a lot of energy, and it's going to a place where it's going to have less. So it's got to get rid of that energy somehow. It gets rid of it in the form of giving off a photon. And so the greater the energy distance between those energy levels, the higher energy, all right, shorter wavelength, higher frequency photon would be produced or would be given off or would be emitted. And so that gives us an idea of why energy is given off from a chemical system. So we must know that luminol somehow is having electrons move from lower energy levels to higher energy levels. And then when those electrons come back home, come back down to the ground state, it must be giving off that energy in the form of those blue photons that we see. That's actually kind of cool, all right? And you see this all the flippin' time, okay? You may not realize it, but the result of all of these different things, these different phenomenon, is the result of electrons moving around in either atoms or in compounds, and they move around based on the light that's striking it, or the energy that's being fed to it. So here we have what's called a discharge tube. Discharge tubes are very commonly used in sciences for educational purposes, because the energy levels in a particular atom are fixed. All right, all sodium atoms have the same energy levels at the same energies. And so the movement of electrons, those transitions, as we would call them, result in the same color photons, the same wavelength and frequency of photons every time. So if we have hydrogen, for instance, and we put hydrogen in one of these tubes and we apply a high electrical potential, a high amount of electrical energy, you will get that tube glowing at a distinctive color or series of colors that are tied to the energy levels in hydrogen. Same with helium or nitrogen or whatever it might be that we're exciting with electrical energy and getting photons off. It's like a fingerprint, those colors. We could identify the element that way. And we see that with neon tubes as well. You put a particular gas in there, you apply a high electrical potential to it, and it starts to glow. Why does it glow? Because the electrical potential, all right, the electrical energy moves the electron further away from the nucleus to a higher energy level where it doesn't want to stay. It wants to come back down to the ground state. And when it does, it loses that electrical energy in the form of a photon, which can be red or green or pink depending on what type of gas you have placed inside those tubes. And it turns out you can play different games with them. One of the things that I didn't put on here, but you probably all have is somewhere, is a fluorescent light bulb. You probably have a fluorescent light bulb, those long tubes. You certainly would see them in Heim, in Lynn Science Center, probably in the Academic Center as well, if you were in there. Those long white tubes. In those, you can actually play around with the color that's being given off, because the particular gas that they put in those tubes is mercury gas, which gives us ultraviolet light, which is invisible to our eye. It's very high energy. And then you coat the tube with something that when it's struck with ultraviolet light, the electrons are forced to higher energy levels. When they come back down from those excited state to the ground state, they'll give off different colors of light. So you can control what color of light comes off of those different tubes. So you could make a tube that gave off only red light if you wanted to, which would be kind of cool. Now you might say the crayon's not glowing at all, but the crayon is absorbing photons. And by absorbing particular color photons will dictate, the absorption of photons will dictate what color a particular compound will be. So for instance, if something is orange, it means it's absorbing blue from the spectrum primarily, and if something's blue, it means it's absorbing orange from the spectrum. If we have something green, it's absorbing red. If we have something red, it's absorbing green. So it absorbs its complementary color. And so all that has to do with the movement of electrons. We don't always have emission like we have in these two cases, but here the absorption is causing the color. So we know a little bit about photons and how light is produced from a chemical system.